Calorimetry is an interesting topic to do experimentally, but it's not particularly interesting to do from a theoretical point of view. It's not that complicated if it's just presented to you on paper, but actually trying to do it in lab is much more interesting. So when we have calorimetry, we're actually looking at the exchange of heat between two systems. And if we know one of the systems pretty well, this allows us to actually make measurements on the other one. The idea is that the systems are in thermal contact with each other, and that can mean, for instance, that we're dropping a penny or a rock into water. Obviously, if the penny or rock is in the water, it's in thermal contact. Then we isolate the systems from the external environment. And again, in this case, we mean thermally isolated. So that would be making it really well insulated. So what we're doing is making sure that no heat can enter or leave between these systems and the environment. So any heat exchange is only happening between these systems. So if we think about the heat in system 1 and the heat in system 2, if these are our only two systems, the heat leaving system 1, which would be negative, must be the heat entering system 2, which would be positive Q. This means that the magnitudes are the same, and we can say that the net Q is equal to 0, that one of them's negative, one of them's positive, they're equal in magnitude. Now, the reason we write it this way is we can actually have more systems involved, though we don't typically worry about that. And again, this could involve phase changes, and that's why we always think about this in terms of Q. It's important to note that we're not talking about change in temperature, right? Remember that heat is an exchange of energy. And so I typically say exchange of heat, but again, heat literally is the exchange of energy. So what we don't say is that the decrease in temperature of one system is equal to the increase in temperature of the other system. That's not true because these two systems can be different masses, they can be different materials, so that means they have different specific heats. What's actually true is that Q1 equals Q2 in magnitude, but opposite in sign. So decrease in energy of one equals an increase in energy of the other, and we call that exchange of energy heat. So that's all calorimetry is. It's an experimental situation where we're examining heat. So how do we approach calorimetry problems? Again, we want to have the systems as interacting with each other, but they're isolated from the larger environment. So you might have, again, a system and a limited environment, but those would just be then two different systems. As always, you want to list your information and identify what you need to find. Make sure that everything is in SI units, which is always going to be important for all of our thermal and thermodynamics problems. Make sure that your energy conservation here is that the heat for the sum of all heats is equal to 0. So again, heat is positive if it's being added to the system, increasing the energy. Heat is negative if you're removing energy from a system. And again, you might have more than two systems, but not normally. Then you want to think about whether your system is undergoing a temperature change and a phase change. If it is doing both, you need to think about both of these terms. Otherwise, you might only have one. Make sure that you get your signs right. Make sure that you have the mass correct for that system and that you've identified your specific heat or your latent heat for that type of material. And again, you might even have multiple phase changes. You might be taking a solid to a liquid to a gas. That's okay. Make sure that you think about the temperature changes along the way and both phase changes. And ideally then, your final temperatures are going to actually be equal, right? That usually what we assume is that they come to thermal equilibrium. That means that our two systems have the same final temperature. Otherwise, they would still be exchanging heat. Now that means that one system has gotten colder and one system has gotten hotter. If it looks like both have gotten hotter or both have gotten colder, you've definitely done something wrong. So that final check is really important. And again, I'm not stressing too much about calorimetry because this is really a special application of everything else we're talking about, and I think it's most interesting to look at it experimentally.